Hello everyone, and welcome to another session of Computational Algebraic Geometry. Today we're going to talk about solving univariate polynomials. So if I give you a polynomial, let's say p of x, and for simplicity let's take p with rational coefficients. Now what does it mean to solve for a root of px? So we want to find, well, in principle an algebraic number, but we can just see it as a complex number such that p of alpha is 0. Now, actually, I'm putting a lot of weight on this word, and it will be very important to understand what does it mean to find a root. So you might think it silly, but in fact, it's a delicate notion, because if you don't define it right, then this problem is impossible. And this is what I find very surprising, that in general, especially in the pure math curriculum, you rarely learn how to find the roots of a polynomial. In fact, you learn that it's impossible to find the roots of a polynomial. And here's what they say. So there's Galois theory, which studies symmetries of algebraic numbers. And Galois theory says that it is impossible to represent alpha in terms of radicals of integers. And here, impossible in general. So I'll say a few more things about this. But it's impossible to represent alpha exactly using these radicals, so expressions like this and their combinations, and you can nest radicals. So for example, cube root of 2 plus square root of 5 would be fine. So you can use representations like this to create many interesting algebraic numbers. But Galois theory says that numbers that can be formed like this have a particular kind of symmetry, and in general, the kind of roots of a polynomial have a different symmetry. And Galois theory says, therefore, it's impossible to represent most numbers like this. Let's say a few words about this part in general. So in general means, first of all, if the degree of p has to be greater than 4, and so one way to say it is that, and then you say, when you fix a degree which is greater than 4, then for most coefficients of ai, you expect this kind of behavior, where the roots of p of x will not be represented by radicals or sequence of radicals. So Galois theory is certainly one of the most beautiful subjects. However, this is where you stop when you are studying the roots of a polynomial. And what we want to do is to change the notion of find and go beyond representing numbers with radicals. So after all, our goal is not to solve the roots of a polynomial, find a good representation, and then put up a picture of this number on our walls. So we want to use it. Therefore, as long as we're able to use it, and in particular, as long as we're able to use it rigorously, so we don't want to just approximate the solution. Somehow we want to have an exact representation, so we would like to be able to do rigorous arithmetic. As long as we're able to do that, I would consider it that we had found the root, as long as we're able to calculate with it. So let's briefly recall what we have for low degree. So if degree of p is 2, then I can write p, so let's change the coefficients. I'm going to write x squared plus bx plus c, so that we have this high school formula that says the roots, I have two roots, and they're equal to minus b plus and minus b squared minus 4c divided by 2. First of all, we're okay with finding complex roots, so this, what is inside the square root can be negative. And this is an example what Galois theory wants to find. So it wants to represent roots with this square root symbol and combinations of such numbers. So here there is actually two very interesting things. One of them is that for every polynomial p, I have a uniform representation of a solution. So that's amazing. So I just look at the polynomial, I don't think about it, I take the coefficients and then plug them into this formula to get both roots. So this is super powerful. And what Galois theory is saying is that it's even stronger, let alone a universal formula like this that's valid for every polynomial. It's just there isn't even a representation that has this format. So you simply cannot use radicals to represent the roots, let alone have a universal formula. So I'm not going to write it, just Google it. It's a very interesting story. For degree p equals 3, there is again a closed formula in terms of the coefficients of the polynomial. Same with degree p equals 4. Perhaps this is why it was very surprising that the behavior suddenly stops. So after having closed formulas in terms of the coefficients, universal formulas, suddenly the structure breaks. Okay, so even before Galois, actually, this never stopped anyone from solving polynomials. The fact that this kind of representation is impossible. And now let's first think about approximation. Okay, so I would like to say that approximation is not solving. So we need extra structure so that we can say an approximate root really somehow is an exact representation of a root. So we need to say a few more things, but nevertheless, let's just first talk about how we could approximate a root. And the idea is this. So let's write p of alpha. So remember, alpha was the root of our polynomial. So this is just 0. I'm going to do the following. I'm going to write this as a Taylor series expansion at some point, presumably close to alpha. So what this would be is that if I'm approximating at some point, let's call it beta, I would first evaluate my polynomial at beta, then I would evaluate the derivative at beta, and I would compute alpha minus beta. And then there are higher order terms. So because it's a polynomial, in fact, this would not be an infinite series, but we can keep doing this. So this is just Taylor's theorem. But here's what we can do. So let's be a little bit crude, and let's just say that alpha and beta are very close by, so that since the second term will involve higher order derivatives, so this will look like beta prime prime beta times alpha minus beta squared, and so on. If alpha minus beta is very small, its square is even smaller, and then this is the general trick that the remaining terms should be negligible. Of course, you can be rigorous here, but let's not be rigorous. Let's just say these are very small, so that if this is small, so that means alpha minus beta has absolute value that is much smaller than 1. That's the notation. Then the 0 should be approximately right-hand side with higher order terms killed. What that means is that if I were to solve this equation for alpha, I can get a representation of alpha in terms of beta. So let's assume this derivative is non-zero. Then this is a linear equation. This is a constant I solve for alpha. You get alpha is approximately beta minus p of b beta divided by p prime of beta. So we've been sloppy here in both killing the higher order terms and dividing by this derivative. So for example, if this derivative is non-zero but almost 0, if it's very small, then we're in trouble in dividing here because it might amplify the error terms here. Okay, so without pursuing the details right now, we can convert this into an algorithm in approximating the root better and better. So the idea is this, that if beta was somewhat close to alpha, this expression should be even closer. And perhaps if we repeat this again and again, we'll get arbitrarily close to alpha. Okay, so here's the sloppy version of Newton's approximation algorithm, which is that you start with some number beta. Well, a priori you don't know whether or not it's close to alpha, so you start with something. And then you replace beta with beta minus p beta over p prime beta. This, by the way, is a rational expression. So p was a polynomial, p prime is a polynomial. So this is just a rational expression in terms of beta. It's a quotient of two polynomials. So you evaluate this rational expression at beta. And then you substitute the value of beta for this number, and then you repeat. So you constantly evaluate this rational function at its own values. This is some kind of a discrete dynamical system. And then if the value of beta, so if this value stops changing, then you stop. Let's call it the sloppy Newton's algorithm. Now this is really a cornerstone of numerical approximation and of scientific computation. And there's a huge variety of ways to improve this. And there are many problems. So the fact is that this is so simple implies that there are actually many problems that you have to take care of. So some of the problems that we were rather careless with, such as the error terms here and the error that appears upon dividing, all of these things can be controlled. It requires work, but you can understand what's happening here, and you can even deduce the following. So if alpha is a root of px, but also it's a reduced root, so x minus alpha divides p of x, but x of alpha squared would not divide p of x. Yeah, so the zero scheme it defines is reduced at alpha. So if this is the case, then for beta sufficiently close to alpha, the distance between beta and alpha upon executing this algorithm improves quadratically at every execution, at every step. That means the number of digits of beta approximating the digits of alpha doubles at each step. So that's amazing. So here, let's explain this a little bit better. So if beta 0 was what we started with, beta 1 was beta 0 minus p of beta 0 divided by p prime of beta 0, and beta 2 is beta 1 minus p of beta 1 divided by p prime beta 1, etc. Then you say that there exists an m, some constant, some positive constant, such that alpha minus beta, let's say n plus 1, this is m times alpha minus beta n squared. So if this was already small, when you square it, it's extremely small. And then the next step, you square this yet again. So it would be 4th power and then 8th power. So it's very, very impressive, this convergence rate. And what is considered to be sufficiently close can be determined, but I won't say anything about it today. So what you do in this case is the following: that when you have a good enough approximation of alpha, since the repeated execution of Newton's algorithm will rapidly refine your approximation, we will see how it works, we will say that a beta sufficiently close to alpha is a solution. So we've found a solution when we have gotten this close. So first let's make a definition. We're going to say that a neighborhood of alpha consisting of such numbers where the Newton's algorithm has this quadratic convergence is called basin of convergence. So a neighborhood of alpha, so that would be maybe a ball around alpha, some radius, maybe r. So this would consist of every number that is of distance at most r to alpha. This is called, so here remember this alpha is an algebraic number, so it is the root of a polynomial. So I'm just going to refer to the same p. If for every beta in this neighborhood, so here this quadratic convergence rate is defined exactly like this, so that repeated applications of Newton's algorithm will have this distance decreasing with this exponent 2 here. And I'm going to apply Newton's algorithm to the minimal polynomial of alpha. And we can declare what we have a solution when we are given a point in the convergence basin for alpha. So a beta in a convergence basin is called a good approximation of alpha, and we will consider such a good approximation to be a solution to the polynomial. So this seems sketchy, but we will see later how basically when you have the ability to approximate arbitrarily well, then you can actually do rigorous calculations with algebraic numbers. Next thing I'm going to do is to show some examples using Magma and to see what kind of things can go wrong. So right now we've made a very, very simple observation. We don't even know if it works very well. We'll see that it fails basically in every way imaginable, even in very simple examples, so that it actually is something of an art to get it to work properly. I should say that approximating roots, or in general numerical methods, have a bad reputation in pure mathematics for being non-rigorous, well, precisely because of the kind of things that we did here. So you can be sloppy, and well, let's say that 80% of the time you arrive at the right answer. On the other hand, so everything I've done here about these approximations could have been made rigorous, and moreover, you can find when you are in a convergence basis, even when you don't know the root, and you can detect this rigorously, right? So all of these things which are sloppy and can be done quickly can be restricted slightly so that your algorithms become slower. You have to think a little bit more, but then everything can be made rigorous. Okay, so now let's play with Magma. So here's what we're going to do. We're going to try a couple of examples and see how Newton's algorithm works in practice. So you'll see that we also hit some obstacles that are not even apparent theoretically. So what I'm doing is that I'm just defining a univariate polynomial ring. So the thing with Magma is that if you don't specify the number of variables, you automatically create a polynomial ring with one variable. The name of my variable is x. I created the polynomial x cubed minus 2, and I have in my mind the cube root of 2. So that's the solution I want to approximate. I just created here the rational expression x minus the polynomial divided by the derivative of p. Let's come over here and then copy into Magma. So this is t. Yeah, and what I want to do is to repeatedly apply the map t to a point that's close to 2. Let's say 1, sufficiently close. So here's my loop. So I start with 1, and I'm going to do this evaluation 20 times. So for n from 1 to 20, I have xn. I declare xn to be the evaluation of t at xn. So I update xn. So in my mind, I start with, this is x0, and then I start with x1, and then I go to x2, that kind of thing. And I'm timing how much this is taking, and I print out the number of the step that I currently on. I'm going to evaluate the polynomial p at my approximation. This is going to be good enough to judge how close xn is to cube root of 2. So you can think about why this is so. So I'm going to make this evaluation, and then I'm going to coerce this to the real field with 10 digits. So I don't want to approximate things to hundreds of digits. I just want to get an idea of how close I am. So the order of magnitude of this distance is important. And then, and here's the catch, I'm going to print out how many symbols it took to represent the rational number xn. Let's see what it looks like. All right, here we are. So first of all, when we started at 1 and after the first step, we were a distance of 0.37 from the cube root of 3, so up to some constant. And then the approximation got really good. So here at the third step, I'm already about 10 to the minus 5 away from cube root of 2, and then 10 to the minus 10, then 20, then 40, then 80. You see the doubling of the number of digits that correctly approximate cube root of 2. So that was because we are now in the quadratic convergence base. On the other hand, let's have a look at these terms here. So that at first it took only 3 symbols to write the rational number xn, then 5, then 14, but then it's getting serious. So look, here we're about 2 million. It took about 2 million symbols to write xn, and that was at 14th step. Therefore, it was taking way too much time to just compute the evaluation of a rational function, because it was exactly evaluating a rational function. In this case, it had 726,000 symbols to represent xn. This evaluation took 1 second, and then the other evaluation was taking too much time, and I stopped. In fact, let's look at xn at 14th step. So this is the 14th approximation. And, well, this is what you get. Yeah, so basically it's not a very good idea to use rational numbers to approximate like this, because the rational numbers, as they're getting better and better approximations of the root, the rational numbers just blow up. All right, so the previous problem seemed perhaps a problem of luxury, because we were already approximating our number cube root of 2 to, I don't know, hundreds of digits. So let's try something more serious. I'm just going to set my initial point to be minus 10. So maybe we don't know where our root is. We just start with minus 10. And now it really gets choked up quite quickly before it starts approximating the cube root of 2 very well. Okay, so I interrupted this computation at the 13th step, because already the 13th step took 19 seconds. And you see here, again, we had about 2-3 million terms in our rational number. So this doesn't look good, and look, this is the error. Basically, we were nowhere near close cube root of 2 at the 13th step, and our computations are choking. So already it cannot operate with such rational numbers. This means that we have to change our approach a little bit. We should not use rational numbers, we should use floating point real numbers. Floating point means you use a real number, you write down a digit expansion to 100 digits, and you always cut after the 100th digit, rounding it up there. So this means that the size of your numbers is constant. So let's do this so that you don't have this rational numbers growing in complexity indefinitely. You cannot have this since you truncate. So the only thing I changed was to substitute minus 10 with a floating point number. Here this was coercion, and this 100 means use 100 digits. Okay, let's do this again. It was instantaneous. So after 20 digits, you see this is the time it takes is 0. All the computations were suddenly instantaneous to 20th step, and we started to get close by. Maybe I should increase now the number of steps since I can afford it. Let's do 30. Again, instantaneous. Well, every step was instantaneous. The errors after the 26th step are 0. That means it's beyond our ability to judge since we're operating with 100 digits. For example, the 24th and the 25th were already at the limit of our precision. And we can see what xn is. So this is xn. Yeah, so we know this is about 100 digits approximation of cube root of 2. Okay, so we see how this is working. Let's look at a couple of problematic cases. So we've looked at cases where it worked. So I've written a small function that just does this loop. What it does is I called it newt, and it takes as input a polynomial, so p. It takes an initial value. For example, this was my initial value in this loop. I tell it how many steps it should do. So this iterate, that's goes in here. So that's the loop part. And I also added a verbosity. So I don't always want to see this information about how many digits I'm using and how close I am, that kind of thing. So that's the verbosity flag. All right, everything else is just the same. And let's copy this into Magma. Okay, and so I would like to consider this polynomial, which is also very simple, but I think you can notice that it's going to be problematic because this doesn't have any real roots. So it's x squared plus 1. And now maybe you can guess already that, well, I mean, it has roots, plus and minus imaginary numbers, but perhaps you can just look at the rational function that we're using. When you evaluate this rational function at a real number, the output is a real number. And then you iterate, you evaluate it at its output, it's still real. So that no matter how many times we use the Newton approximation, we will get a real number. So there's no way we're going to approximate a root. Yeah, so let's see what happens. First, with this is init, that's the initial value. So I'm going to take 10 steps. Let's see what happens. Okay, so 10 steps. It first got down close to 1, which means x got close to 0. And then it jumped back up to 2, then it grew fairly large, and it looks like it's getting small again. Let's see if we were trying to do it a few more steps. So let's increase it to 20. I think you can guess what's going to happen. We're going to hit a problem that we've seen before. Okay, so first of all, it's taking a lot of time already, and it looks like we're oscillating around small, moderately small numbers. But it was kind of chaotic because at the beginning, it got small and then blew up to 9,000 and then got back down again. And let's look at the following. Instead, let's start with 1 and let's see what happens. So my initial value is 1. I'm going to take 20 steps. That's my plan. And I say go. And it crashes. And you can so read the error. It says, while trying to evaluate this rational function t, it says the denominator that I had is not invertible. That means the derivative that I used was 0 when evaluated at xn. In other words, we hit, of course, the derivative of x squared. So x squared plus 1 has derivative 2x. So it means my xn was 0. So I managed to hit this point, and then Newton's operation just blew up. So I could not continue. And this also explains what must have been happening in our previous operation when we started with 10. You see, we got very close to 0 since this was our error. This x squared plus 1 was this number. So x squared was small. That means the derivative was large. And then we can suppose that that's what caused this blowing up. Okay, so we saw basically the first problem. Well, we saw two problems. One of them is that we cannot approximate a root sometimes. Let's make a note of this. Sometimes we can't get close to the root, right? And the other thing was sometimes we hit a point where the derivative vanishes. And then Newton's iteration blows up at that point. So this is actually extra problematic because we already saw that we cannot really do exact computations with rational numbers because then the numerator and the denominator blows up. So we will do approximate computations. That's very common. And if you're doing approximate computations and you get near a point where the derivative blows up, then we will get a huge number that will distort your errors. So I mean, remember that if you're working with a floating point with 100 digits, basically the 100th digit is just noise. It's just random because things have been rounded up. And then as you add things, multiply them, whatever, these last digits just become noise. And then if you get close to a point where the derivative vanishes, you end up scaling maybe with something like 10 to the 100. And all you get is then noise. But it is nevertheless true that for most complex numbers, so if you start with a complex number as your initial point, then you would hit the root. And this is true, and we can see this too. So let's maybe say, let's take the complex field with 100 digits. In fact, let's take 30 digits. I don't want to fill the screen. And I think 10 steps should be enough. And where should we start? So maybe 1 plus I. So I is just the imaginary number in my complex field. And I'm going to start at 1 plus I. I'm going to do 10 iterations for this polynomial. Let's see what happens. Okay, so now I plugged in 1 plus I to my Newton iteration. And you see that very quickly we are reaching the root of our polynomial x squared plus 1. Yeah, so as long as we start with quote-unquote random initial points, we should be fine. That's the general philosophy. But there's one more thing where failure is possible. So now this is similar to what we have seen with x squared plus 1, but less obvious. And this is what might happen to you in practice. That here, because we knew what was happening here, maybe unless you plot it, you won't see it. Now let's do the same kind of thing. Now I'm going to take this polynomial, start with 1, take 10 steps, and maybe this won't be very informative. So what I'm going to do is take I steps for I from 1 to 10. Yeah, so this function returns the ith approximate. Let's see what happens. Okay, so first of all, it's pretty much instantaneous, but now let's look at the approximations. I'm oscillating between 0 and 1. Yeah, so this is a little more surprising and uglier, and it just shows you that Newton's method is not foolproof. If you start with nice numbers, clean numbers like 1s and 0s and whatever, then actually this is it's very likely that Newton's method will fail you. Okay, so if you want this method to succeed, you need some kind of random number generator, basically, to seed your Newton functions. Okay, so let's look at what Wikipedia has to say. First of all, the Wikipedia page for Newton's method is very good, quite comprehensive. And they already have a picture of the algorithm. So what we've described algebraically can be described as follows. So you start with an initial guess x1, you evaluate your function there and compute the tangent. And go to the point where the tangent hits the x-axis, evaluate your function there, compute the tangent, go to where the tangent hits the x-axis, and repeat. And then with this, we can explain, for example, what happened when we stuck at the 1-0 loop. For example, this 1-0 loop is here, so this was the function x cubed minus 2x plus 2. You see there's a complex root here somewhere, but because it's not real and we're evaluating at real functions, something like what was happening with x squared plus 1 happens, and we get stuck in a loop here. And in this particular case, if you start with 0, you go up, evaluate your function at 0, compute a tangent vector there, tangent direction, go up to the point where it hits the x-axis, you set your new value of x to be 1, and then go up, compute the tangent, and see that it hits 0 again. So you get stuck in this loop. There's also this fun object called the Newton fractal. So this is the Newton fractal for the function x cubed minus 1. So you're looking at the 3 roots of 1. So this is the complex plane, so that 1 is here. The root with positive imaginary value is here, and negative imaginary value is here. So what these regions indicate is that if you start on a red region, you will end up approximating the value 1. If you start at this red region, you'll jump around and then eventually come back here, and then you'll be in a convergent space and you'll approximate 1. So, but you see this fractal-like behaviors. For example, here the green region is extremely close to a red region and a blue region. And so if you perturb your initial value just a little bit, you might end up here, or if you might end up over here. So it displays chaotic behavior with respect to your initial values. So when you're near a convergence basin, then the behavior of Newton's method was perfectly understandable. So it converged quadratically, but outside the behavior is chaotic. And in fact, this region or the boundary is a fractal. So it gets arbitrarily bad. As you zoom in, this image repeats. All right, this is where we will end today. See you at the next lecture.